So today's discussions, like we are going to discuss about this RF front-end design, and on that, like I'll be touching upon like maybe the overview of what is actually RF front-end design, and like when we mention about this transmission line, how it actually impacting those transmission lines. I mean, particularly when you are going for design. So basically, we are going to discuss about what is RF front-end design and what exactly like physically how it looks like, and why it was actually made and how do you actually make it. And after that, I'll try to correlate like what is the transmission line, what is the actually action or maybe the role it play on this RF front end designs. And specifically, like I'm going to talk about maybe kind of I'll try to deduce how the Iron Man movie was made. So basically, I'll try to put an analogy like what you call whom you call as a product, what is called a prototype design. So if you remember the Iron Man movie, so the first sequel is about the prototype being the complete box. Then after that, if you see the all the sequels, it's all improvisations and different type of skill sets. So the similar way we are going to talk about this RF front-end design, what is the prototype, how it looks like, and when you say that my prototype is ready, and how you will make it a prototype to be a product. And when you say any particular thing as a product, right, what actually it means whom you call product, how the product gets rejected, even though it is working functionality wise, it's working very well, and it has proved all its skills, but still it is not on the market. So that particular section we will discuss very detailed, and how it will actually matters you if you don't know or not aware of this particular this product certifications or SEC regulation at particular like when you're designing this RF front end. So with that, actually, we will will conclude it. So before going to the RF front end design, so this is a typical the, the world. Let me put my. So this is what we all are actually surrounded by. So if you look at like I think uh, everyone have the different type of RF electronic devices and surrounded with a different type of frequency bands. And in today's world, if you look at like all are talking about 5G and IoT devices, because that's what is going to be, and all the engineers in full demand. I mean, you need to know what are the things to be followed, and you need to understand like okay, what is the requirement of the customers and how that will change the life. So if you look at it, this is uh, uh, one of the article came like by 2025 we will have 30.9 billions of IoT devices surrounded. So if you look at today's world, so we all are surrounded by the smart car, smart TV, smartphone. I mean, even like some of the houses are coming as a smart house. So all are actually interconnected. Even if you look at the medical devices, also are giving a very good stuff to connect to the from rural to the urban areas. So we all are surrounded by this all RF devices. So when we mention about RF devices, it means that it's a RF means nothing else is a radio frequencies, which starts from low frequency to high frequencies. So when we mention about low frequency, particularly a device which communicates to the outer world, it starts from 50 megahertz onwards to till your maybe 100 gigahertz. So if you look at from AM, FM to, I mean, from 90 megahertz onwards, if you look at this as a communicating device, so it ends with all the 5G mobile phones and further, which actually works on 28 gigahertz, 77 gigahertz, and also they're actually looking for 95 gigahertz. So we all are going to be surrounded by all these RF devices. So when we mention that RF devices, it means that they are completely RF front-end design. So that we will go very detailed. But what are the actually challenges like when you mention about that we are surrounded by so many devices? It means that all the devices are actually interfering each other, and they are not actually disturbing the functionality as well as the communication service. So that particular also we are going to discuss that even though we have surrounded with a different type of devices with a different frequency and operation functionality, so still we are actually shielded with a safety wall. Now coming to the RF front-end design, so this is how exactly you will see the very generic block box where actually they are talking about this RF front-end design. So if you go to the baseline of RM front-end design, so basically they are like connected to the three basic equations. So if you follow the, I mean, if you want to build an RF front-end design, these are three basic equations you need to follow. The first is channel capacity, which talks about the channel capacity and how, in what rate you are actually trying to send the data. Then after sending the data, how those data are actually going the signal to noise ratio, that how much it's getting corrupted and how they are getting actually retrieved from after receiving it. And in between that, this particular equation tells about like how much data are actually going to lose. So when you transmit from one point to another point, so that the distance may be a 10 meter, 3 meter, 10 meter, or 3 feet, or maybe hundreds kilometers. So based on that and the different type of environments, we are going to actually design this RM front-end design. So basically, RF front-end design, nothing else like your, if you try to put an analogy, like if you in the earlier days, if you're trying to send any message over a stone on a paper, right? So you try to actually wrap the paper on the stone and try to throw it. So now you have a different type of equations. Let's say like you want to send that, you want to throw the paper, stone from one point to another point, or maybe first floor to the second floor. The amount of power actually it requires to reach, right? So that that will be the one of the thing you will say that transmitter part. But at the same time, at the second floor, if somebody is waiting to receive it, how it's going to be received? Let's say like if the stone is destroyed the message, what will happen? How will retype those messages and try to understand what is written in that? So similar way, this RF front-end design also designed. I mean, like if you look at like this is the this particular part is called your intermediate frequency, where actually it deals with the message part. Then it goes by the carrier frequencies. This particular, what I'm talking about is amplify the power required from first floor to the second floor. So this particular is a power amplifier with a particular filter design, and it goes to the antenna. So basically in the RF front-end design on the transmitter side, you have a up converters. So that's your message is like wrapped on the stone. Then through the stone, you are actually throwing to a certain distance. So that takes care with the power amplifier. Then at a particular way, I mean, you want to actually filter it out so that it will reach to a particular person. So we are actually using a filter. Then it goes to the antenna. So now going to these particular terminologies like this power amplifier, bandpass filters, and antenna. So these are three different terms. So let's say like power amplifier is nothing else, and it amplifies the signal so that it can reach to the longer distance. So if you look at any Bluetooth device, like like current scenario, they mention about like this particular Bluetooth device can work within the 3 meter or 10 meter. It means the amount of power it can amplify is within the 3 meter or 10 meter. And at the same time, the amount of the antenna can actually send the data to within that reach of 3 meter or 10 meter. So it depends on like at what distance actually you want to cover. So at the same time, when you transmit, so we actually this particular part will be the receiver part. It means that you have received with another antenna, and by having a switch. So you just, this is a particular RF front-end design for a transceiver. But if you are actually designing transmitter and receiver separately, so this particular section will be your transmitter part, and this particular section will be your receiver part. So once you receive from the antenna, so it actually similar way it segregate using the filter. Then again, so whatever the amount of power, amount of message you have got, so it might be feeble after reaching maybe the long distance. So it has to be amplified using the low noise amplifiers. So that's called as LNA. Then again, it starts your A to D converter, or you say so it is just like you see up converter and down converter. So up converter actually digital to analog conversion, and here it is like analog to digital conversion. Then at the signal system, so you actually receive the data and you make it into a message. So this is the typical behavior or the building block of an RM front-end design. So now coming to how it looks like. So I have just taken one of the board from the TI. So basically, if you look at like this, will be around 3 to 4 centimeter in size. So basically, this particular area is the main IC area. Though maybe the others are the mechanical stuff. So you are seeing the different type of board. I mean, if you open your mobile phone or if you're any notepad or anything, so you will be seeing this similar kind of stuff. Maybe you will see so many blocks, but this is a very basic transceiver design. So you can see here one of the port is written as an antenna port. So here antenna is not yet joined. So this is particular in PCB. So this is will be your RX input and this is the TX output, right? And they are called this coaxial connector, and it joins to the total transceiver system. So similar to here what we are seeing it. So basically this is the part where you if you try to correlate. So this is a particular part that relates to your antenna positions. So here actually you need to actually place the 2.4 to 2.5 gigahertz. Means this particular is Bluetooth transceiver. So the Bluetooth antenna has to be joined. So there is a concept called half duplexer or full duplexer. It means that so you having this half duplexer like the walkie-talkie phones, like you will receive first and then after that you will transmit. So it is like one by one, or there will be like full duplex at the same time. So you will try to send transmit and receive at the same time. But here in this case, like you can use actually two antennas. So mostly if you look at on your mobile phone, you won't see two antennas. Generally you will see only one antenna. So that's they are called as full duplex transceiver, right? So but in generic, like if you see any long distance communication, so there you will see there will be two separate sections. One will be a transmitter section, another will be the receiver section. But when you try to reduce to very high frequency applications, and particularly like Bluetooth or Wi-Fi module, so you will see that one antenna will act as a transmitter as well as a receiver. So they will have a wideband antennas, wide bandwidth, so which will actually make them accommodate both transmit and receiver frequency at the same time. So you mean like if you compare to your mobile phone, so we are not going to wait maybe at like we need not to wait for the receive the message, and we need not to wait for the other side also. We need not to wait for our transmitting the message. So that's how the transceiver works. So here you could see like this all I mean connected. They are connected to antenna, and it goes to the a kind of a filter, so which actually segregates the message signal. Then it goes to the middle as a processor unit. So that's what how it is look like. So you can see it has an LNA, then it goes to the local oscillator, which will mix with the RF frequency, then segregate into the IF frequency. From the IF frequency, it will further it goes to your signal system. So this is how the receiver is working. The similar way, if you look at the other side, so that is the transmitter part. So it comes from the modulator part. From modulator, it goes to the local oscillator, and from local oscillator, it goes to the power amplifier. So basically, the power amplifier is, as I mentioned, that it sends a signal to the long distance. But if you look at like the common variant, like when you go for very high frequency, so the distance between that will actually reduce. If you look at like your GSM frequency actually works at a longer distance, while if you look at the Bluetooth or Wi-Fi, they have the strong channel capacity, but they are a limited coverage. So that is the typical things we will go through. So this gives you, I hope like this gives you an idea about how this RF front-end design. So in this discussion, we are not going to talk very detail about what is a power amplifier, what it actually looks like, and how we will design it. We are not going to like discuss about what is the upcoming power amplifier or band pass filter or antenna is going. But we will understand like how this RF front-end design is going to be work, and what are the things we need to consider. So let's say like an engineer comes with an antenna, power amplifier, band pass filter, and up convert. Can we make it as a transmitter? So for that, like what are the things is needed from each section, and when you make it a complete, means when you try to fill all the blocks together, and when you make it as a system, how actually it's working. I mean, how do you define this system is working, or the next word will be how this prototype design is working. Then when you make this prototype, and how we will make that prototype design into so-called product. So this is a typical the building blocks for this Max 2830. So the transceiver design which is used for this Bluetooth block. Now coming to this RF front design. So let's go to the next slide. So which actually tells about like what are the companies are working on those on this particular module. As I mentioned, you like each section comes from the different engineers. So one engineer cannot make all design together. So there will be different sections who actually deals with only the power amplifier. There will be other section will be there who will be working on this band pass filter, also called this mask impedance design. Then another engineer will talk about like different type of antennas. So let's say if I want an RF transceiver which is working for the 5G. So what do you mean by that 5G? It means that you are going to deal with different type of frequencies with a different skill set. Let's say like you are going to deal with a GSM antenna which works at 800 megahertz and it goes to 7 gigahertz. So it one module you will have all those frequencies and their respected components to be designed within a specific area. So that's the challenge for the engineer, like how we will accommodate so many components together in a small. So if you compare to the older mobile phones to the the current mobile phone, the drastic reduction in the size is from because of the standards are what are the upcoming technology actually make it like slimmer and thinner, even lightweight. So here actually you see the power amplifiers come from these companies. Actually they deals with that, and so these are the receiver modules which comes from that, and most of these the basic components come from those particularly we say this discrete part. So when you are going to deal with this RF front end supply chain, we need to understand how do you choose a component. Means this particular slide talks about like how do you actually choose, because you are going to design RF front end or the system design. So you are not going to build all together from your side. You are going to actually acquire all those components, and while acquiring those components, what are the things you should look at it. So I mean, before purchasing it, that's the like how you see, like before purchasing, you have to list out like what are the behavior of these each component has to be. Now coming to the each section. So as I mentioned that this RF front end design is used for like amplify the message and send to the longer distance, but it has its own restrictions. One of the restriction is like minimizing the distortion. So what happens like, and these all these components are active device as well as the passive device. But what do you mean by this active device and passive device? So passive device, it means like they might be a lossy, but their behavior will be a constant. I mean, their behavior will be very much linear. It means that if you look at their graphs like voltage and current behavior, so it will be most of the things will be linear. But when it comes to the active devices, particularly let's say an amplifier and power amplifier, so their behavior quite changes over the time and also over frequency. So let's say like you are designing a power amplifier which will be working at 800 megahertz will be way different the power amplifier which is designed at the higher frequencies, because of the stringent rules and the stringent the microsystem, or I will say the fabrication restrictions, and also the cost. So when you mention about like I'm going to design a 5G, it means that you are actually going to design from low frequency to high frequency, and you are accommodating all the component in a small place. So why that restriction comes there? Because the cost. So when you goes to the higher frequency, there is a very direct formulas are there. So when it goes to the higher frequency, the size of the component reduce drastically. So if you look at your old radios, which was working at 80 megahertz to 110 megahertz, they're quite bulky. But nowadays, like you could see those radios are like kind of a slim set, right? So it means that I mean their working frequency is same, but because of the component reduction, size of the component reduction, so they fit in within the range and it becomes very cheaper. So if you look at 1970s and 80s, if whoever have radio, there seems to be like kind of rich. Even if you have the dial phone, so there seems to be like all rich people, because that seems to be very costly. It means that you don't have that much money to accommodate so many components. But now if you compare to the similar kind of components which is reduced in size as well as the cost drastically, and you can accommodate as many. And also at the same time, the product has to be very much reachable to all within the reach of I mean the price as well as the behavior of the device. So here, so as I mentioned that this is like means when you're designing the transmitter, we are actually looking for the minimize the distortion on the transmitter side. So that will be taken care by this by low noise amplifier, and as well as that you will go to the matching circuits, which will comes together and it reaches to the antenna. At the same in the similar way, if you go to the transmitter side, you will try to see if you go to the receiver side, you will try to see the nullify the noise. So there it will be a distortion at the transmitter side. It will be a distortion at the receiver side. It will be kind of you are receiving the noise, and so those noise can be environmental noise as well as the system noise. So as I mentioned, these low noise amplifiers are kind of active devices. So they have their own noise, which will actually mix with your data. And before it goes to the demodulation or A to D conversion, so it get amplify the noise. And so at the same time, at the receiver side, you won't see any, either you won't see any data or you maybe see a noisy sounds. So sometimes if you look at earlier days, one of the very simple example, right? Earlier days, whenever you try to take your phone near to the any mic, so you might be hear some buzzing sounds, right? But nowadays, if you see, such sounds are not there. So the basic difference was there, like actually it is getting mixed with it mixed with the receiver side signal and get amplify this low noise amplifier, and it goes to the A to D converter, and along your voice or whatever the signal you are actually supposed to receive, you are actually receiving the noise. But that is completely filtered out because of the impedance or because of the filter and the very high noise figure of the low noise amplifier behavior. So that we are actually filtered out, or basically we are chopped those noise and we are receiving the actual message or actual voice. So that's the change. I mean, that is what the role of this noise on the transmitter side. So at the same time, so when I mentioned about like we are going to design a 5G transceiver one set, so it means that over the band of frequency, as I mentioned, that is going to work on different bands. So it has to have flat phase. I mean, all these active components have flat phase and gain throughout the bandwidth. So if you look at it, it may not work at so from 800 megahertz to till 7 gigahertz, but it has a kind of a particular bands. Like the GSM works at 700 to 910 or maybe 960, based on the location or the geographical positions. At the same time, if you look at that, I mean, Bluetooth works at 2.4 to 2.5, and your Wi-Fi works at 5 to 7. I mean, again, it depends like where you want to actually fit in the your set. So that's why you need to have flat phase and the gain. It has to be linear behavior. So that is one of the challenges while designing both transmitter and receiver within the specific area with a less cost. So apart from the design restriction, there is something called, we say that, crosstalk. It means that let's say we both are talking over a phone, but both phone has it shouldn't be interfere each other. Means what do you mean by this interference? So it means like, let's say I have a transmit a signal and there is two receivers are there, let's say RX1 and RX2 at the same distance, but my intention is to send to RX1. At the same time, RX2 also can send me a message which is intended to me, but instead of it goes to RX1. So that's called the interference. It means what I supposed to send the message to RX1, but due to the interference, it receives the RX2 message. So that's how we call it is crosstalk between the within the system or outside the system. Like when you design a RM front end design, like particularly mobile phone or notepad, so you have a different type of like system within the box. So we can say multiple system, and it is quite possible that okay, I have my own design RF front end design set where you have multiple system, and you might have also this RF front end design with the multiple system, and they may start interfering each other. So this is one of the second challenge we will see, like when you have this kind of particular terminology called multiple input and multiple output. It means that you are transmitting the signal to multiple receivers, and at the same time you are going to receive the signal from the multiple transmitters. So that time this particular topic comes like how they are actually interfering each other, and it is basically it actually uh, 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 basically it will stop the functionality of the system. Let's say like, okay, I want to send you send something, but you are not receiving at all because you are trying to send from transmitter to receiver, but because of the interference, the receiver showing like, okay, I didn't get any message, or maybe you are showing like, okay, whatever you have got the message, it is get corrupted. So maybe we come across such thing like when you're trying to GP some message and we're trying to send it, it says like your data is corrupted. So that's how this interference plays the role. So basically, it actually means provides the functionality of the system. So that's why we need to be very careful while designing this transmitter and receiver. Now, if you look at overall, behavior. So basically, we need to see in the RF front end design, we need to check like what are the transmitters and receivers, the 4 points, right? So this digital analog conversions, how the power application works, and what is the bandwidth limitations. So as I mentioned that if I'm going to design it from low frequency to high frequency, what are my restrictions? Like, can I use one power amplifiers for all the frequencies? No, it is not possible. So you have to use power amplifiers for each particular frequency. Nowadays, it has come up like you have the multiple frequencies power amplifiers. At the same time, you may have multiple frequency low noise amplifiers, and so that the similar way you have a restriction over the band pass filter on the multiple frequencies. Maybe this particular section antenna we will discuss in the later slides. So antenna plays a major role for RF front end design. So if you look at like means actually we are surrounded by one of the physical existing body called antenna, right? So if you look at your from the dish antenna from your TV to if you go to the older days antennas where you will see a kind of a standing structure called monopole antennas, and the older TV antennas and TV transmitter, TV relay center where you will have a huge dish antenna. So all actually plays a major role. And how do you choose actually the antenna? So if you look at your mobile phone, so if you open your mobile phone, particularly the backside slip, right? So you will see a one particular design which is at the top. So it will be a kind of a multiple like rectangular shape. So which will actually called as a PIFA antenna. It's like a kind of a folded antennas are there, and it is actually working from 800 megahertz to till 5 gigahertz or 6 gigahertz. It covers all the frequencies from GSM, LTE, GPS, Bluetooth, and Wi-Fi together. So that is one of the challenges. Like, how do you actually design this antenna and accommodate it inside your mobile phone or notepad or iPad or anywhere like. Okay. So if you see when I mentioned about IoT device, so there it is the biggest challenge. Like, how do you design your antenna? Because you cannot make your antenna bulky. That we will see like how can be an antenna will be bulky and how over the generation how it actually reduces. So apart from this antenna, so if you look at the RF front end design, so they are actually like these are the few things we need to check, like system gain. How is the system gain over the frequency? How the system noise figure? As I mentioned, like each active devices has their own noise, so actually it impacts individually. And apart from that, you have a restriction of like how much noise you get from the environment. So that's how we can find out this noise figure. So particularly this input third order intercept points. So it is like the point at which the output noise level is sends to the power of the third order. I mean that relates to the how the power amplifier actually works. So there we will see at the third order intercept point. And as I mentioned that particularly this power amplifier has to behave like a linear because they are the active devices. Over the frequency, their behavior changes. So as I mentioned that when we go for multiple frequencies over a bandwidth, when we are planning to design, so this particular power amplifier or this low noise amplifier actually behave very weird because of the restriction over the design. So this is the one of the challenging part while particularly designing or choosing the component for the system design. So similar way, the receiver, the spurious free dynamic range. So that's basically the bandwidth which we are covering. So there how the behavior. So basically these are the numbers has to be known before we're designing the RF system. As I mentioned that In one of the slides I showed, like different companies are showing the selling the components. So before choosing the components, these are the few things we need to check out, like how their behavior individually. Then when you accommodate them in a block manner, so how additional noises are actually added to the system, and are they are within the limit or not. Now, if not, then functionality wise, your prototype design is failed. So in case if it is passing, then how it is actually affecting, like when you convert this prototype design into the product. So that we will discuss in very detail. So apart from these stringent rules from this front end design, so when you design your prototype front RF front end, so when you try to place it and see this functionality, it also depends on like how is the environment. So what do you mean by environment? Is it so there it comes like, so will this RF front-end design will work in Antarctica, or will it work in very well in Sahara like desert? Because there is a variation on the temperatures. So if you look at those, as I mentioned, one of the movies this in Iron Man, right? So there is one particular scene is there where it get failed. It when it goes up to the sky, it get frozen out, right? So there actually this the discrete components behavior quite differ when the temperatures changes from normal room temperature to the frozen state or very high temperature. So there, if the capacitor didn't behave like a capacitor, so it will behave like an inductor. So over the temperature, so that's why the complete system will get failed. So before design this RF front end, you need to understand how the RF, the environmental behavior comes there.